Okay, our next presentation will be given by Ranis. Okay, uh, am I right, Ranis? Okay. Okay, Sergi. Okay, thank you. And the presentation is about the modeling liquefaction in floating offshore wind farms. And okay, the floor is yours.
Thank you very much for the introduction. So, I'm not the first author, that's my colleague Ranjit. He's responsible for this project and he did the most of the work. Henry Krusche is the supervisor, and I was not involved so much in the project, but I will present his work because he couldn't attend the open forum workshop. He had actually a meeting for this Infinity project. So what is it about? It's an abbreviation, the Infinity, and it stands for Integrated Designs for Future Floating Offshore Wind Farm Technology. Basically, it's about floating offshore wind turbines. The project is quite big. It's a European project. There are 13 partners from 8 countries, and you can see a map here. So we are from Wiki, from Germany. There are universities, but also companies, wind turbine manufacturers, and so on. Total budget of the project is 6 million euros. It's set up for 4 years and started in January of this year. So basically, there are so many partners, and the goals are summarized somewhat here. I just mentioned our part. It's mainly about the foundation, the anchor of the offshore wind parks, and the modeling of this anchor, and also about the score. But you'll see it later. So, what is liquefaction? I have 2 pictures here. The one on the left shows the camera is submerged into the water and shows the seabed of an ocean. Here you can see it's this line. It's where a pipeline was buried in, but at some point it liquefied, and the pipeline got floated, and it got off the place, the location where it's buried, and it's now somewhere here. Hard to recognize, but the whole pipeline was just thrown away. Another picture is from Japan, 1964. There was an earthquake, and liquefaction may also happen. In this case, it happened due to waves. In this case, it happened to the earthquake, which are also waves, actually. But the ground liquefied, and you see here the tilted buildings. So that's also one example. Yeah, what is the liquefaction actually? It mainly occurs in the loose, fine marine soils. How it works, so the application of waves builds up the pore pressure in the soil, and at some point the effective stress is reduced to zero. So the soil doesn't hold anymore. The soil particles start to move with respect to each other. Soil loses its capacity, and it cannot withstand load. And load may be an anchor or a pipeline, right? Afterwards, after the liquefaction, there is a compaction process where the soil particles get again together and compact. So let's see this in a diagram and some pictures here. So here the soil particles, there is some water trapped in between the particles, and it's some kind of solid structure like this, right? It's actually the seabed. What happens when you apply waves? You can see here on the y-axis we have period averaged excess pore pressure. So it's the pressure inside these pores between the particles, and it starts to grow, right? You apply pressure, and the pore pressure also grows, and this pore pressure may get so high that it pushes away the solid particles, right? So this one, you can see here, that's the phase where the soil liquefies. So there is no structure anymore because everything has gone pushed away. But after this, the particles settle down. It's a compaction, and then compact to a solid structure. So we have some phase change here from solid to liquid and again to solid. What's the motivation? I mentioned it earlier. Here's also one picture. So we have a wind turbine here, and if seabed is a bit farther away, how it's tied up to the seabed, there is a gravity, so-called gravity anchor, tied with some ropes, and it's pretty heavy, and yeah, the whole thing about the part of our work in this project was to model this gravity anchor. You can see it here. So we have soil, gravity anchor, and gravity submerged into water, soil underneath, and there are some regions which liquefy. So how do we model this? We don't model the water as it is. It's here we've got a boundary condition. It's a 1D wave equation actually. Here we've got some soil regions and liquefied regions. These are the governing questions, and they are quite colorful because what you're certainly familiar with are the red ones. So that's the liquid region. The blue ones is the solid region, and the black one is both. It's applied in both regions, solid and liquid. And you can see there are parts of each region, or both of them, in almost every equation, right? In continuity momentum equation. We have also drift flux equation for the particles, and linear momentum and pore pressure accumulation. So yeah, what's pore pressure is, it's shown here. It's this part which grows, right? If the wave are applied, so this P continuous is coming from the waves, and it's accumulated in this pore pressure. Here are the boundary conditions. So we have at some point we will have a liquefied region here. So it doesn't liquefy all at once. It's a process, right? We have some interface or boundary here between the liquefied and the solid region. And here is because we have this interface, we need some. In this case, it's a buffer between the two regions, and we need dynamic mesh in order to make it move down, propagate through the domain. So we calculate the liquid accumulated pore pressure. Then we have some liquefaction criteria. If the region is liquefied, we have phase identifier, and identify the phases where we need to put the buffer into, and we have a topo changer which creates this buffer boundary, and then we modify the mesh. And this one is actually a video. Can you play first video? So just a video of the propagation of this boundary through the domain. So it starts to liquefy here, and it propagates. You see, it's this is like this line actually on the faces of the cells propagating down. Okay, thank you. You can switch again to the slides. There are some properties here for the seabed, wave properties. For the wave, it will be important in a moment. There is a wave period and the wave height, H. Pressure build-up properties, and we need some properties for post liquefaction. There is a second video. So in this one, you will see the process of first, it's a soil in the initial state, the yellow one which you saw. Then it liquefied. The process you see now is actually the compaction. Liquefaction is much faster than compaction, and here in this legend is the compacted soil. Yeah, perfect. It's not liquefied now. It liquefied. This red area is actually liquefied. There are wave, it representing the wave, just for the representation, right? And now it's compacting again. And this area above, so after the compaction, you have higher density of the soil, right? So above you got water, and now down is the soil. Okay, so here are some results. It's a diagram, time diagram on the x-axis, and the pressure on the y-axis, and it's a validation. So we compare the experiments to the numerical results. And as you can see here, so wave period is 1.7 seconds. The height is 0.2 meter of the waves, so it's about the waves. Here, the different colors identify different depth of the location where we validate the results. Like 0.05 meters underneath and so on. And as you can see, the agreement is quite well. So we have again, this one is actually the liquefaction. There is a detail here. It's a zoom in this region. So it liquefies here, and then it's liquefied, and then it compacts again. Right, and here we have a representation how much what's the error actually of the numerical result, and it's quite good here. So we have it also for the wave height of 15 centimeters for different period, wave period, 1.5 seconds. It's also quite well. It was not so good for another wave period of 1.3 seconds, as you can see here. So the dashed line is the experiment, and the solid line is the simulation. And it compacted much earlier than the experiment one. And it needs the model needs some fine-tuning, so there's calibration in this case. So it's about part of the drift flux model. There is this Q criterion here, and if you tweak it a bit, you will somewhat increase the time of the compaction. And yeah, after this treatment, so of the Q parameter, we got also pretty good results. So in these models, also fine-tuning is involved. All these results were presented without gravity anchor. So the soil may liquefy also without any load, right? But our interest is, of course, to do it with a load. So it's coming here on top. And by now, we don't have the validation here, so it's only the results of the simulation and only of the liquefied region. And we used here 3 different masses of 12 kilograms, 4 kilograms, and yeah, there are also two kind of simulations. One is stationary, so the anchor just lies on the seabed, and the other one is forced. It simulates the wind turbine, the impact of the wind turbine above the sea. If there are waves, then wind turbine moves and it pulls on the ropes at the anchor, right? So anchor moves a little bit as well. We actually also did this, and as you can see here, it has quite some impact. This forced, it shouldn't be neglected. Yeah. So to summarize this, we developed a simulation which can model residual liquefaction and compaction processes. It requires a minimal number of input parameters. It utilizes poroelastic solid model in the soil region, a Newtonian fluid model in the liquefied region, and then dynamically changes the boundaries in between. The model shows very good agreement with the experimental data, and it can also effectively predict pore pressure built up also in forced conditions. We need to validate more, and another outlook ongoing work within the Infinity project is simulation of score. And just to give you some pictures, what is it about? So we've got this gravity anchor here on the seabed, and as you've seen in presentation before by Professor Yasak, the sand may move here and build some go around this anchor and displace it, or I don't know, tilt it. So it's then there's need for some protection measurements against this process, against score. And that's the ongoing work in the Infinity project. So thank you very much. I will be glad to answer your questions.
Okay, time for questions. Okay.
Thank you for your presentation. I wonder, how do you deal with the air phase? When the wave is including the air and water, yeah, how do you deal with the interface between air and water phases?
That's easy. We don't deal with it.
So,
we don't include it into the simulation.
So the wave is only a wave boundary?
Yeah, it's only the boundary.
So how do you deal with the top boundary? When
okay.
you
yeah, it's already gone. Sorry. Can you show it again, maybe?
The wave boundary is only the inlet or outlet, but I wonder how to deal with the top boundary.
Yeah, I got your question. So basically, we don't even deal with the boundary of between the air and the sea. We don't look into this. We just look at the boundary between the sea and the soil, right?
Oh, I see.
And so air is completely neglected. The water, to some extent, also neglected. And this boundary between the sea and the soil, there we have this. Let me show you. Yeah, there we have this mud line, right? And there we apply this wave equation at the mud line. And this one is only here presented to for better representation, right? But we don't use it in the simulation.
Oh, I see. I got it. Thank you.
Okay.
Okay, thank you for your report. This is very great. I wonder that why did you choose dynamic mesh? I think your equations show that the alpha can show the difference of different phase. So why did you choose dynamic mesh? Thank you.
Okay. I should mention again the work is not from me, from Ranjit, so he's a better partner to ask. But as far as I know, they maybe consider it, but you've got a lot of numerical errors, right? So if you've got both phases in one cell, then you'll get numerical diffusion, and for this kind of simulation, it's no-go. It's damaging. You need some interface at the faces for proper convergence.
Okay, thank you very much.
You're welcome.
Is there any other questions or comments? Yeah.
So in your validations, you are showing the agreement with the experiments, but much better is on the solidification part. In the liquefaction, there is some delay, whereas in your model it goes straight up. Are you more interested then in the solidification, or this liquefaction is depending on initial conditions? So what's the reason for not good agreement for the liquefaction?
So you're talking about the results here. Okay, about this detail. I wouldn't say it's okay. Depending on the case, right? This one agrees pretty well, right? For my extent, and you have to look for the time scale, right? So I suppose it's not this. The agreement in time is not so important. It's important what's the pore pressure will be, the highest one, and the most important part is the question: will it liquefy or not? So these are the most important questions. About the agreement here, yeah. Okay, you're talking maybe about this one. Yeah, that's some seconds. I'm not sure how huge of an impact this disagreement has. You know, that's again, if you're interested in this, write an email to Ranjit.
Okay, due to the time schedule, I think we can stop here. And thanks again for the speaker.